Okay, this is November 16th, practicing some AP past exam problems. We'll start with multiple choice, work our way into free response if we have time. So obviously I numbered these on my own, but if you look at the number next to the actual problem, that helps you decide if it's on the no calculator or the calculator part. So number 6, anything from 1 to 30 is no calculator. And then anything that's between, I think it's 75 to 80 or something. No, 70 to 85. I don't know. The bigger numbers are calculator active, okay? So I can look up the exact numbers. I just forgot what it is off the top of my head. If they're low numbers, lower than 30, no calculator. If you want to make those marks as we go, you can. You don't have to. No calculator on this problem. All right, so let f be a function defined above. Which of the following statements about f are true? It has a limit at x equals 2, it's continuous at x equals 2, and it's differentiable at x equals 2. All right, so first, I would just check if there is a limit at x equals 2. So looking at my function, you have a piecewise, and it's defined for x squared minus 4 over x minus 2 for everything except when x is 2. So I want to see what it's approaching. You don't need to do left hand or right hand here because it's not defined for 2 different values when x is less than or greater than 2. But I want to see what my function is actually approaching and then see if it is 1, and then I can decide if there's a hole or not, okay? I can't direct substitute, right? I get indeterminate form. So a strategy I would use here would be to try to factor. Those cancel. Then I could direct substitute. All right, so we get 4. So I don't know exactly what this looks like, but I know that as my function is approaching 2, the limit is 4. So it looks something like this, and I know that at 2 it's 1. Okay, so I have this removable discontinuity here. So there's a limit that exists, right? It's 4. Is it continuous?
No.
No, and therefore it can't be differential either. Okay, discontinuity would be one of our 4, so just be A. Just I. Okay, good stuff. Good review. Next problem. All right, again, this would be on a no calculator part since it's numbered 11. Don't really need a calculator for this. The graph of f is shown above. Which of the following could be a graph of the derivative, f prime? All right, so I know my graph of f is a cubic, so its derivative is going to be 1 degree lower. It's going to be a quadratic, right? So that automatically eliminates c. All right, now we have to look at for characteristics of my graph. So at all the horizontal tangents, so these points and these points, what characteristic do I have on the graph of the derivative? X-intercepts, good. So the ones that have x-intercepts there would be B and D. So that eliminates A and E. And then the only last thing we have to check is when our function is increasing here. Increasing from left to right, my derivative would be positive values. Oh, shoot. And then when I'm decreasing, which is in between those, my derivative would be negative. So that would be B. Because D is exactly flip-flopped there. You can see it's positive derivative values for when it's actually decreasing. All right, feel pretty confident you could have got those ones right. Those aren't bad, right? All righty. Next one. Another no calculator. In the xy, just a normal coordinate plane, the line x plus y equals k, where k is a constant, is tangent to the graph of y equals x squared plus 3x plus 1. What is the value of k? All right, so we have this line over here. I'll kind of tackle that in a second. But I see tangent to this graph, and that tells me, hey, I'm probably going to have to find my derivative, right? So let's do that quickly, which is just 2x plus 3. Okay. I'm trying to think where to go from here. Our derivative is 2x plus 3. Why do I? Oh, I know. Okay. If you rewrite this in slope-intercept form, here is our line that's tangent to the graph. Now, this is obviously linear. So what's the slope of this line? Is -1. So you want to figure out where your derivative or your slope equation has a slope of -1. Okay, so we use that information to set my derivative equal to -1. So I'm trying to find like what point right now. The line is tangent to the graph. Solve this quickly. It looks like I'm getting x to be -2. Perfect. Okay, there's our x value. So we're trying to find this constant. So right now we know -2. So you're solving this. You're like, okay, I'm going to have to figure out what y is. And to find that, you can just plug it back into the normal equation, which is y is x squared plus 3x plus 1. So it's tangent at this point, -2. Okay, times the value that without the calculator, you get -1. So it's tangent, it's like point of tangency is -2, -1. So you can plug that in for your y value here and then solve for the constant. Kind of a weird problem. And again, it's like the calculus part of that wasn't hard. It's just get used to kind of how they phrase something. So I have -1 plus 2 plus k. So our constant would be -3. And yes, that's right. Okay. So using the slope from that equation to set it equal to our derivative. That was a little tricky. I don't like the wording of that one, but all right. So far, my derivatives have been pretty straightforward. Let's try another one. Ooh, this is a good one. This one's kind of a tough one. Okay, no calculator again. Let f be the function defined above. So we got a piecewise function here. C and D are constants. If f is differentiable at x equals 2, what is the value of c plus d? Okay, so they're telling us our function is differentiable. Differentiability implies that it's also continuous. We'll need that maybe later on, but just note that anytime they're giving you the information it's differentiable, you can assume it's continuous too. So we know it's differentiable at x equals 2, so we can start by just finding the derivative of our piecewise function. We haven't done a whole lot of piecewise functions with derivatives, but you just basically take the derivative of each piece. So the derivative of cx plus d would just be c. The derivative of x squared minus cx would be 2x minus c. And your domain pieces for each piecewise function stay the same. Okay. So this is going to help us. We know it's differentiable at x equals 2. So we know that coming in from both sides to 2, so we'll go 2 from the left of the derivative, which we would use c, is the same as the derivative coming in from the right, coming into 2 from the right, which I would use this piece. We know this because they told us it was differentiable, so we know that their slopes are coming in at the same point. And again, the reason why you want to do this, anytime you see a piecewise function, you're usually looking at like left and right hand limits. All right, so you can solve for c by plugging 2 in for x on that other side. So you get 2c equals 4. C is 2. Okay, now you notice like our d variable dropped out when we took the derivative. Now I have to find the value of c plus d, so I need to solve for d, and that's where this differentiability implies continuity comes into play, that if we know it's differential, that also means it's continuous. So we'll just straight up look at the limit, not the derivative, the limit from the left to the right, and we'll be able to solve for d. So this is for continuity. Okay, this we've been doing since chapter 1. The limit as x approaches 2 from the left, I would use this piece. And now we know that c is 2, so we can just go ahead and plug that in. Has to be the same as coming into 2 from the right. And this will allow us to solve for d. Okay, x is 2. So over here I get 4 plus d. Over here I get 4 minus 4 is 0, so d is 4. So to answer the question...
Maybe -4.
Oh, -4. Yep, good catch. -4. 6 wasn't even enough. All right, so to answer, obviously, c plus d, -4 plus 2, we get -2. Okay. Another kind of tricky thing is like you might be tempted to like start with continuity, but anytime you know it's like differentiable, if you can show it's differentiable, since differentiability like implies continuity, like you want to do that first. Okay, because if you can like kind of show this, then you know it's gonna be continuous. Or vice versa, like if you know it's not differentiable, like start with showing that it's not continuous, and you're obviously like, okay, it's not differentiable because we know it's not continuous. If that makes sense. All right. Okay. This is just a straight up instantaneous rate of change problem. Obviously, this would also be on a no calculator, so you got to practice kind of doing this math mentally too. Here is my function. Find f prime of 2. That just means find the derivative. Instantaneous rate of change. 1x is 2. So start by finding the derivative. All right, -8 x to the -3rd plus 1/2 x plus 4 would drop out. Then I just need to plug in 2, f prime of 2. All right, here's where you got to practice doing this without your calculator. I don't know why I plugged in -2. It's up to 2. Okay, 2 to the -3rd is not -8, right? That'd be 1 over 2 to the 3rd, like that. Or you can think of it as like 1/8. So we end up getting -8 times 1/8, -1. However you need to mentally think of doing that math in your head. 1/2 times 2 is obviously 1, so we get 0, which is D. Not bad. I like the next problem because it's a good kind of check on notation. What does d dx mean? Derivative with respect to x, yep. Probably going to need to use quotient rule, too. I see a quotient here. Yep, d dx. That's just telling you find the derivative with respect to x. Obviously, I'm just with respect to x. No MDiff, none of that funny business. Quotient rule, low d high. Derivative high is 1. Minus high d low, 2x. All over low squared. All right. simplify the top a little bit here. You have x squared plus 1 minus 2x squared plus 2x. Don't multiply out your denominators, especially like looking at my answer here. You can see they leave it in like that factored form. All right, x squared minus 2x squared negative x squared minus 2x. Putting this like in standard form up top, plus 1. Good, that's our answer. All over x squared plus 1 squared. See? Yep, see. Nice. It's a classic quotient rule. Okay. Another piecewise one. You can tell from doing like practice problems, like AP exam loves to throw in piecewise functions a lot. That's because they're the interesting ones. They are where we have those like jumps and removable discontinuities and all that good stuff. Okay, another no calculator. I wonder if there's actually any calculator active. Not for multiple choice. Usually if they're just straight up asking to find the derivative, they're not going to give you your calculator. Especially at an instant, because we can use our calculator to find that. Alrighty. If f is a function defined above, then f prime of negative 1 is... Alright, let's find the derivative. The derivative of the top is just 3. Derivative of the bottom, negative 2x. Okay, the pieces don't change. All right, so just like before, I'm going to have to check to figure this out for this piecewise. The left and the right hand limits of the derivative. So the limit as x is approaching negative 1 from the left, I would use 3. The limit as x is approaching negative 1 from the right, I would use negative 2x. And then I go and I plug in my negative 1 with direct substitution. And I get 3 is equal to 0. And again, this is like multiple choice, so you don't have to show your work. You guys probably didn't need to go through all that work to show like that limit's going to be, or that derivative's going to be 3, right? It's a line. Okay. So if you like know that and you like check the derivative of the bottom, you see, oh, they're not the same. So the limit doesn't exist. Non-existent. The slopes are coming in, so it's creating like a corner or a cusp. The slopes are coming in at 2 different values from the left and the right. Ooh, I like the next problem. Gary, overuse that saying a little bit.
Only on these.
Okay, here's my function, x over x plus 2. What points, x, y, on the graph of f have the property that the line tangent to your function at the point has a slope of 1/2? Okay, so I see again that line tangent to f, and I'm thinking derivative. Instantaneous rate of change. The slope at a specific point, okay? I'd probably do product rule here. Or not product rule, sorry. Quotient rule. I was going to say you could do product rule if you wanted to. I'll do quotient rule. So low, d high, minus high, d low. Derivative of low is just 1. All over low squared. Okay, let's clean up the top a little bit. I have x plus 2 minus x. I end up with just 2 over x plus 2 squared. Okay, there's my derivative, my slope equation. And I want to know when these have a slope of 1/2. Well, if this is my slope equation, I want to figure out when they have a slope of 1/2. I'm going to set it equal to 1/2. To solve this, a couple of things you could do here. I times both sides by 2 right away. No, I don't want to do that. I'm going to divide both sides by 2, actually. That'll get rid of this 2. Or you could cross multiply. Maybe I'll do that. Maybe I'll cross multiply. Sorry. You could do a lot of different things. Yeah, this is probably easiest. Cross multiply. Solving for x, I'd square root both sides. Don't forget about plus or minus. So we get plus or minus 2 equals x plus 2. Parentheses. Subtract over 2. All right, I get x values then. Negative 2 plus 2 would be 0. Negative 2 minus 2 would be negative 4. Now, I know it told us to find the points. But looking at my multiple choice options, the only one that has x values of 0 and negative 4 is choice C, right? So after we find those, we can really just save time and not go any further. We could obviously find their outputs by plugging it back in here. But this one is the only option that have x values of 0 and negative 4, so it's C. If you had time to like check and make sure, you could, but that's a good like test taking sure you kind of have to be like trying to work through as quickly as you can. And again, your work is not graded with multiple choice, so you can kind of be like as sloppy as you need to be. Oh, Jason, that's gonna be hard for you, isn't it? Just your bubble sheet is graded, nothing else. And we should have some practice sessions of you being sloppy. You gotta work fast and sloppy. Okay, here's a good problem. Given a function, find the instantaneous rate of change at 4, aka the derivative. Classic check on power rule. So I'd rewrite it as powers, just like that. X to the 1/2, and then 3x to the negative half. No calculator again. 1/2 x to the negative half. All right, here we go. Minus 3/2. 1/2 times negative. Oh, negative 1/2 times 3. X to the negative 3/2. Now, however you need to like rewrite this, if you want to move the x's in the denominator, you can, if that helps you before you plug in the numbers. So you could do this. I think that would probably help me. I would probably do that first. We have to plug in 4. So x to the 1/2, it might be easier for you to do that. Math, square root instead of the 1/2 power. Okay. Let's go over x to the 3/2 power. So anytime you have a rational exponent, your denominator is like the index. So if it's a 2, you're square rooting. If it's the denominator is a 3, you're cube rooting. The denominator is a 5, you're fifth rooting. And then the numerator is what you're raising that power to. So this would be like the square root of x. No, I'm plugging in 4. The square root of 4 cubed would be how you do that math. Do you guys remember when you learned fraction exponents? I'm just curious in general. Is it algebra 2 or is it Calc?
No.
You don't remember. Okay. We usually did it in algebra 2, but. Okay, so here I have 1/4. And here I have, so the square root of 4 is 2. Cubed is 8. So 3/16. And again, this is no calculator. So you have 4/16 minus 3/16. We get 1/16. Right? Yeah, that's right. 1/16. Is that an option? It is. Good. Okay, we did it right. 1/16. I feel like fraction exponents come up a lot with like derivatives because they give you like square roots and cube roots. Ooh, it's straight one finally. All right. If y equals the sine of x times the cosine of x, then at x equals pi over 3 dy dx, that's notation for what? Derivative. Derivative y with respect to x. Yep. So, dy dx. Don't forget about product rule. we'd have to do first times the derivative of second, negative sine of x, plus second times the derivative of first. Might I add, this would be a no calculator question. Okay, so we get negative sine squared of x plus, derivative of sine is cosine, plus cosine squared of x. This is not our Pythagorean identity. That's sine squared plus cosine squared, so it's not just automatically going to be 1. We're actually going to have to plug in pi over 3. I'm going to switch up the notation here just to show I'm plugging in pi over 3. Okay. Pi over 3. So it's really 60 degrees. So if I needed to know that, there's pi over 6, pi over 4, pi over 3 is this one. So we go 3, 2, 1, 3, 2, 1. All I care about is this one. There's my pi over 6 one. Or sorry, pi over 3, which is 60 degrees. Pi over 3. All right. So the sine of pi over 3 is my y-coordinate, square root of 3 over 2. So I'm going to have to square that. And it's negative sine squared, so it would look like that. Plus cosine squared of pi over 3. Well, cosine is 1/2. I have to square that as well. All right, so here I would get negative 3/4. Sorry. 3/4 plus 1/4. So we get negative 2/4, which is negative 1/2, which is A again. Okay, we'll stop there. Couple more multiple choice, couple more FRQ. We'll pick them up next week in RTI. We're behind others. Damn right.